Today I'm going to talk about modeling aging chains in GoldSim. And what I'll be doing is first walking through a couple of applied example models to demonstrate what you can do with this type of model, followed by showing some different methods of calculating or simulating aging chains in general. I'll show 3 or 4 different types of methods. There are more ways that you can do it in GoldSim, but I'll show just this handful of them, and also talk about the reasons why you might choose one over the other. And this type of model is quite useful for modeling the growth of a population, whether it's just in general a population of people for example, in a geographic region, but also perhaps within an organization. Both of these types of applications have been used by our customers in the past, and much of what I will show you is based on what they have developed. Also, we have internally developed these methods separate from that, as well as just a way to show other methods in GoldSim. Usually the presentations that I give are based on environmental systems, also water management, but what I'll show you today is quite a bit different of an application. However, it could be that perhaps a environmental system model is being driven by population. Perhaps you're looking at water demands, for example. It's a function of population. So it could be that you need to incorporate it for that type of model. But we also have customers that are solely looking at the economics or also just population itself as the problem they're trying to solve. And so these methods I'll be showing are quite useful for that. Okay, so let's go ahead and get started. The model I'm showing you right now is similar to one that's in our library that you can download. If you just go to our library and put in aging chain or population growth, you should find this one. So what this model does, if I go to the top level and go into the dashboard, then run the model, then what you see are 2 charts here. One is showing the female component, the other male component in what we were calling decadal, I guess that's how you pronounce it, cohorts. And what that means is we have separated the population into decades. If I double click on one of these charts to expand it, then you can see the legend appear at the bottom. And what we've done is lumped all of the ages between 0 and 9, essentially in decades, for all the ages from 0 to 100, well, to 99 actually. And these are just sums. The model itself is simulating cohorts of 1 year, actually. So it's modeling every single year as a separate cohort. And when I say cohort, it means a group. And so we have separated the population into groups of 1 year each, where if you're a 1-year-old, then the model simulates you as a 1-year-old until you become 2, and then you leave that group and you go into the 2-year-old group. And that's what the model is doing. That's how an aging chain works. But to roll all of that up, it's just summing these into 10 years to just make it easier to visualize. And even this alone is still quite a bit of information, as you can see. But what it does show is how there should be about a 10-year gap where if you see some sort of rise or drop, then you should see in a subsequent cohort a similar pattern of a rise and a drop. Like, for example, this pink line being the 30 to 39, and then this black line being the group right after that. You can see that they're about 10 years apart. They should be. That the group before starts dropping, 10 years later, the next line starts dropping. Now there is slight variation between them because we have losses and additions going on. Well, in this model, I think we only have losses occurring. The births come in on the obviously on the low end at age zero, and then subsequently there's losses. But in a real model, you might have a lot more going on. You might have migrations of people coming into the system we're modeling, into this location, and also out at different ages. Okay, so let's go into the model and see what's going on a little bit more. If I were to just plot the time history of just all of the cohorts, then what you'll see here is a huge legend, because we're looking at all of the age groups. If I just hide this legend, you can see it's a lot of information going on, and so that's a little bit harder to visualize. But that's why we've added them into 10-year groups. One cool thing you can do with this type of model is use a final value chart to build something that might be like the histogram you might be used to seeing in some cases. And also what you can do is use capture times in GoldSim to look at the final values at different points in time and walk through the model. So I can switch through these different capture times and see how the population cohorts are being populated through time, which is kind of nice to see as it walks through. So also you'll see at the top, I had to inverse the y-axis, as you can see, and then also I had to make the male part negative so that it goes the opposite direction on this x-axis, just for visual impact. But anyway, it's kind of a nice way to look at the population as it's changing through time. Okay, so I won't get into how all these calculations are done here, because I want to back up and go to a simpler model before going into this. But hopefully by the end of the presentation, you'll have a better idea of how this kind of thing works. But you can also download our example from online to see this in more detail. Okay, so another model is one that is being used to calculate the population of employees in an organization in a very simple way. So here's a model that where we assume that new hires come in to the organization at the entry level. We don't have any hires coming in at any other level besides entry level in this case. And the model walks through the process of an engineer that graduates from engineer 1 to engineer 2 after 1 year of working there, and then subsequently graduates to engineer 2, 3, 4, 5, all of those after 1 year. So they're all 1 year apart, and after the engineer 5 year is complete, then they graduate to be a manager. So that's what we're simulating. A very simple setup, but intended to show you the detail of how an aging chain might work in GoldSim. And now this is just one method, and this method is using integrators. And it is also using a new not a new, a specific instruction on a discrete change that perhaps you have not used before. It's probably rarely used, except for in this type of application. So let me show you what that is. That's over here on the new hires discrete change. So this is a discrete change element found up here in the events category of our elements, discrete change. And the discrete change element allows you, similar to all the other elements, to define a unit. In our case, we are using this unit called PERS. I don't think that needs to be capitalized. I think it's by default not capitalized. If I right click and go to units, and by the way, capitalization is it's not enforced in units. However, there are a couple of exceptions to that, where if you use a capital M, then that could mean something different than a small m, where a small m is meters and a capital M is in some cases used to represent a mega for a million. So for example, megaliters. But anyway, if you said capital PERS, GoldSim interprets it the same as small PERS. Anyway, if you go to units and then go to items, you'll see this is a built-in unit that we have, PERS, for one person. We also have K and M for 1,000 and million persons. Very useful for doing population type models. But again, you can always define your own units if you don't like this abbreviation. Maybe you just want it to be the letter P. I think that is still not being used, so you could just say P. Anyway, we do limit the number of characters that are supplied for a unit dimension. So that's why it's abbreviated to that. Next is the value. And in this case, we have a scalar output that we're referring to, and it's just a time series. We're just saying, here's a time series going forward of how many people we plan to hire. And these are all entry level. The next thing is the important part. That's the instruction. Those of you that have used discrete changes before have probably only used add and replace. So add will just put a new value into whatever you're adding this to. So into a reservoir or into an integrator, it just adds that value every time it's triggered. But in this case, we are going to use the instruction called push. And what this does is a bit different. What this does is it says, okay, I'm going to push this value into an integrator. And I'm pretty sure it only, I think it only works for the integrator. It can only be put into an integrator. And when you do that, it will cause whatever was in the integrator to get pushed out. So that's why it's a push. And it works great for aging chain, because that's what we want to do actually. You want to push something in and then push it out the other end in a simple case. And so that's what we're doing. We're taking a value that we get from a time series and we push it in to this integrator engineer one. And we do that whenever it's triggered. And this trigger is based on another event somewhere else called trigger chain shift. And so we can go look at that. If I go up a level, we have this event, just a triggered event that says, do this once a year. And I'm using an elapsed time simulation. So that's why it's E-year. Something to consider, by the way, if you're doing it on a calendar basis, then you would probably want to say year to refer to the calendar year on changed year. But in this case also, we are only starting we don't want to push employees out of their current cohort until after the first year has elapsed of the simulation. And so that's why we have this check down here that's added that says that we need to wait until the simulation has started to move forward in time so that we don't push everybody out at time 0. We need them to work for 1 year before going to the next cohort. Okay, so that's how that works. And the reason I put this event here at the top level is just because there's a chance that maybe I want to change the rate at which we are pushing everybody through the system. Okay, so so you might ask, well, why would we do that? Well, it could be that your cohorts are longer than 1 year. Maybe they last for 2 years in each of these groups. So then you would change it to say, okay, let's only push people through the system once every 2 years, and so you could change it globally there. And also with this method, it requires that all of these cohorts are being graduated at the same rate because of the way that this works. So if that's not something you want, if you have people moving through the system at different rates, then we would need to do something different here. Okay. Anyway, so those are the assumptions that we're making here in the simple model. And if we go to the integrator, then you'll see here we have a couple of things that might be a little bit different from what you're used to. First of all, well, these first few things are probably something that's still common. We have an initial value in the cohort. So you might have an initial population of engineers in that first cohort. And this is just based on a static data element. And we are referring to it as a item of a vector. So the initial population is a vector. And in this case, it's we call it groups, you could call it cohorts, whatever, but it's the number, it has a number of rows in there that are equal to the number of categories here. So we have 1, 2, 3, 4, 5 groups of engineers here, cohorts. And so we could refer to 1 through 5 to obtain the initial value. So this is just how many engineers are in this cohort at time 0, right? Then the next one is the attrition rate, which I haven't mentioned yet. The attrition refers to losses. It's a term used by mainly in the HR world that I'm aware of anyway, where you have losses, and it could be a combination of things, people just quitting or whatever, people that leave. And so in this model, we have a very simple method of saying in all the cohorts, the attrition rate is the same. But you don't have to do it that way. You could have a different rate for each group. But I just refer to the same attrition rate for all the groups. And in this case, it just happens to be 15% losses. So that means we're going to, on every year we're going to remove 15% of whatever is currently in the cohort. And because 15% times the value that's in here will not end up with a whole number, I've rounded it, but you don't really have to do that. We're still going to end up with decimals at some point in this model. And so, yeah, you can't have a decimal or a fraction of a person, right? But I would say don't get too hung up on that with these kinds of models, because it's going to be cumbersome to try to always hold to be exactly integers throughout, unless you go with a different approach, which I will show here in a bit. With this approach, I would say rounding is probably not necessary because you'll end up with decimals at one point or another eventually here. Okay, so we are removing this 15%, and then in addition to that, our new hires are coming in, and that's this push right here. The really important part of this particular model is that we go to the More button down at the bottom of the integrator and check the box for Provide a Pushed Out Discrete Change Output. We need that because we want to have graduates from this cohort move into the next cohort. So you need to have that checked. And then you can go into the next cohort and you see it's exactly the same, except the initial value is grabbing the second row of our initial population, 5 people from the second row. Same thing down here, attrition rate times itself divided by year, and then pushed out. There is a problem or a potential problem here that we have already with this model, and that is this 1 year definition. This is a kind of a bad form right here, right? Because this is just assuming that everybody stays in here for a year. It's assuming that the people being uh, leaving this cohort, that happens in a 1 year period, right? But what if we don't mean that? What if we mean, oh, actually it's 15% of the people are leave that are in that cohort during the time that they're in there, and that time they're in there could be different. So I would say instead of defining a 1 year number like that, I would say use a global input so that can be edited um, globally. All right. Anyway, so we have additions coming in, the new hires coming in, and then losses, and then the graduates that are moving from engineer 1 to engineer 2. So let's take a look at what that is. We have this influence line moving here. We can double click on it to see what it is. And what you'll find, if I expand this, you'll find that we have engineer 1 dot pushed out. So that is a new output that perhaps you've not seen on an integrator. That is a new output. If I click on the output port, you see it is this one called pushed out. It is a discrete change type of output, as opposed to the total quantity within the cohort, right? And that was made available when we checked this box here. Okay, so now we can come over to the second cohort and we can see same thing for initial value rate of change, but the discrete change coming in is this pushed out output coming from engineer 1. We also check this to get the graduates that leave and work our way through the system. Finally, we have managers, which just takes the engineer 5 graduates. And so then we can run the model and look at the results. And this shows the new hires that come in that then feed the engineer 1 group, followed by each of the subsequent groups after that. They all have different starting points, but they eventually work their way through the system. And then you can look at the total population, which is this green line. Probably a bad choice of color. We probably should do something like that for the total. So there's the total population there. We can also plot the retirees because that's just the amount of people leaving the manager role there. Okay, so what you have here then is essentially like a supply chain kind of a model. And instead of just defining add new hires as a time series, probably what you'd want to do is make it a function of the demand for the people that you have in the system, right? So that's typically what people would be doing in this kind of model. They'd say, okay, we project that going forward we'll have some sort of demand. That might be a function of whatever the economy or anyway, various factors, right? And they will need to do a projection because there's a lag in the system. For example, what if you are really looking at, I have a demand for managers? Well, that means you need to be proactive 5 years in advance on your new hires. And so you would have to do a look ahead, essentially. And those things can be easily done in GoldSim. So for example, you could use a submodel that looks ahead for 5 years and says, okay, based on this demand and based on this system, we're going to end up with a gap. If we don't start hiring right now, we're going to have a gap in 5 years. And so you hire ahead of time. And that is exactly what some of our customers have been doing with GoldSim. Okay, So this is a simpler type model, and it's one way to do an aging chain in GoldSim. But now I will open up another model that is essentially going to show you the differences in various methods. Okay, so this model shows 4 different methods, and the one that we just talked about was this one called pushed integrators. If I go into that container, here we are. It's a little bit different example, different names, but it's doing exactly the same thing. But now we have these other 3. So let me start with the material delay type method here. And they're all using the same input data, by the way. I could show you that really quick. Input data. So we in all cases, well, except for one, we have an initial population. And this is just assuming we have 4 cohorts, 4 groups. We also have a cohort duration defined here of 1 year. So you could globally define the duration that people reside in each cohort. We also define a loss rate, which is global, but you could have a loss rate that's different for each cohort if you wanted. And then we have new arrival rates here, which is also just a constant. But I have it as I've put a I've varied the loss rate and the new arrivals using a stochastic. And then I have an event, a global event that is called advanced cohorts. Essentially, this is what causes all of the graduates to move from one cohort to the next. It's what triggers that. All right, so with that, we can go into each of the methods. So here's material delays. If I open that one, here are my 4 cohorts. If you use a material delay method, then likely you'll need to also add splitter elements if you have losses going from leaving each cohort, and usually you would. And so you need to use a splitter in order to remove the portion that is lost before graduates move into the next cohort. And so with a material delay, you get a couple of added benefits, or I guess a little bit more flexibility in some ways, as opposed to the pushed discrete change that I was showing you earlier. So with a material delay, you're working with flows now. That's just the way the material delay works. And you also need to consider the material delay in terms of um, uh, conceptually, that is, in terms of a conveyor belt, where you're adding something, some sort of material in a flow, as a flow, onto the front end of the conveyor. And then the delay time that you specify for this element, that's down here where it says delay time, that is the time it takes for this, whatever material you put on the front of the conveyor, to travel along the conveyor to the other end. And then it will discharge off the end of the conveyor at a flow, as a flow. That is the main output of this element, is whatever is flowing off the other end. That's the main output. And when I say main output, I'm talking about, if you click on the output port, that's the name of this element, also shown here. Main element, main output. That is going to be a flow. So just remember that. Different than what we were talking about earlier, which was a discrete change, right? So now we have a flow, and in our case, we're modeling people. So this would be a flow of people coming off the end of the conveyor. But we also have another output called amount in transit. So those of you that have worked with discrete or with material delays, you know that there's an amount in transit. That is the amount of material that is sitting on the conveyor at any point in time. And that will be an amount, not a rate, right? Because if you're putting rocks on a conveyor, it's that pile of rocks that's sitting on the conveyor while it's moving. And that is precisely the amount that we're interested in when we're doing a model. We want to know how many people are in that cohort during the simulation. And so the material delay is really nice for just conceptualizing that kind of a process of things moving through the system. And so you could even look at this as supply chain sort of as well. But anyway, for material delay, or sorry, for aging chain, it's important that you're linking these material delays together, as we are here. But in this case, we have losses. So let's take a look at this a little bit closer. So let's open up the material delay, and in here we have a rate, persons per year coming in, and that's just all it needs to be is something per time. Usually with aging change, you're looking at people, but it could be items. It doesn't need to be persons. It could be just be no units, in fact. But anyway, we have persons per year. It just needs to be per time. And then the quantity is persons. And then what's coming in? Well, in our case, we only have new arrivals coming in. But the nice thing with using material delays is you could have multiple inflows coming from multiple sources coming in. And that makes it very flexible for downstream cohorts. For example, if you're modeling an organization, perhaps you're hiring people not at entry level, perhaps you're hiring them at different levels. And so this makes it very easy to bring people in at any of the cohorts just by clicking this plus sign and adding new inflows. It's very easy. But everybody that comes in will be delayed by this delay duration. And this is defined globally, but also nice that we can have this be defined individually for each of the cohorts. So that means each of these cohorts could have a different delay time. So that gives you a lot more flexibility than what we were talking about earlier as well. Okay, and then the initial outflow, this is a little bit tricky. So you have to think of this in terms a little bit different than what you might with an integrator or reservoir or pool. Those elements, you defined exactly the amount of people that are sitting there at the beginning of the simulation. Well, in this case, we're talking about an initial outflow. So you have to kind of think of it a little bit differently. Right now, what we use with the material, what you're going to be defining here is the initial outflow. What's coming off the end of the conveyor belt at time 0. So that's how it's defined. So in our case, we'll have to say, well, it's the initial population definition that we have here. And then we have to make it a flow rate. And we'll just say, well, that's divided by the cohort duration. That's also the delay time. Okay, then with that, we go to a splitter. And in the splitter, we're going to just accept the whatever's coming off the end of the conveyor that will then graduate to the next cohort. And this is where you define the losses outside. So then we can put a loss rate here in our splitter, and this is just a percent because that's how splitters work. Splitters work based on a fractional amount, but you can change that. You can define it as an amount instead of a fraction, but I think that would be more confusing because we are not talking about a flow rate here. We are talking about splitting a flow. And so I would say keep it to fractional. That would probably be the easiest to understand. Anyway, so we just define a fraction. In this case, it's 10%, and it's just going to have to be assumed that it's 10% of whatever is leaving the system. Whatever graduates to the next cohort, we're just going to say, well, 10% gets lost during that time. And so it's just kind of baked in that it's assuming that it's a 1-year basis because we have a 1-year duration that the cohort people are in that cohort. So whatever the delay is for each of the material delays, that's what you're going to have to assume is this loss rate is occurring over that duration, because we don't define a loss rate in terms of time in this particular case. So that's something to consider if you're using material delays, this method. The graduates are whatever remains, right? So the splitter just works that way. It just tells you, okay, well, I'm just going to take whatever remains, and that's what graduates. And so I can define these names, which is nice. That way, when I come over here to the next cohort, then the inflow makes sense. It's the splitter 1 dot graduates. It's the graduates from splitter 1. And you could change the name of splitter 1 if you wanted. You could call it cohort 1. I don't know. You could give it a name that has something with cohort 1 in it, so it makes more sense. But anyway, we do the same thing with the delay, and then the initial rate is just looking at that global input row 2 because it's for cohort 2, and we just go along our way, and then we could look at the populations in each of the groups and then the total. And here's a chart that shows that. And then we can look at a table view, and oh, I need to turn off, let me turn off high resolution time histories because we just need to see the values on each year. There we go. So you can see here at year 0, we have 12 people in cohort 1. And then after 1 year has elapsed, then those 12 people have moved into the second column right here, diagonally down. And it's dropped from 12 to 1 because we have some losses. But if I turn on my, if I add more decimals to the table, then you see it's not exact, right? We have some decimal people. That's just something you have to deal with in this kind of model. But I think it's okay. Usually you're working with a lot of people in your models, and so rounding them is not a big deal. You just have to reduce the number of decimals. And this, I'm switching this, you can't see this, but I'm switching this using my keyboard. I'm holding the Alt key down and then using my right and left arrow keys to change this. You can also change the number of decimals up here in the model, options, and then go to results, and you can change that number here. Okay, so that's one method. The next one is pools. We can use pools. Let me go in there. You can see it looks simpler, and this, I would say, is probably one of the most flexible methods to use, especially when you're working with larger populations, and if you have to have a lot of inflows coming from other parts of the system. I would say pools might be the easiest. Well, so I shouldn't say easiest, sorry, most flexible. So let's look at cohort 1. So cohort 1 is a pool, and so we define it with, we're going to be working with flows again, by the way. We define it with an initial quantity, that same input, which is a data array, with looking at the first row of that array, using the 1 right there. And then we go to the inflows and outflows. By the way, a pool allows you to specify a lower bound to prevent us from ever dropping to a negative value. With using integrators, it is possible to drop to a negative value. Although when you're doing it with discrete changes, like I was showing you earlier, then you would be worried about that. But it's something to keep in mind, that it just works that way for you. You can use these kinds of inputs like this, checking a lower bound at 0, just to ensure that you never drop below 0 and not have to worry about it. It's a convenience, definitely. Okay, so we don't ever go negative. We have an initial value, and then we can look at the inflows. In our case, we have new arrivals coming in. So these are new hires. And then we have an outflows where we have losses and graduates. We define those separately. The loss is just the amount of people in this cohort. So if I click on here, you see it's the cohort, that's this element. So how many people are in here multiplied by a loss rate, and you have to define it as, since the loss rate in this case is just a %, you have to divide that by the duration. And this is where I was showing you earlier how I had it divide by 1 year. I typed in the number 1 year, and I told you that that might not be a good way to do it. You probably want to refer to a global variable, which is what I'm doing now, dividing it by the cohort duration. So a loss rate divided by duration multiplied by the amount that's in here. That's the loss. And then the graduates is just however many people are in here divided by the cohort duration. So everybody that's in here, however long we want them to stay in there, they will eventually all leave the system after that duration. If you had shorter time steps, then you would see these people gradually leaving over multiple time steps. if the time step length in GoldSim is shorter than the duration of the cohort. In this case, the cohort duration is 1 year, but if you had a time step of 1 month or 1 day, then the graduates would be leaving, on a consistent basis throughout the year. Anyway, it does give you more flexibility for sure on how to do that. Okay, so then we go to cohort 2, and the only main difference between the first one and the second one is that the inflows, instead of having new hires come in, we're just accepting the graduates. But as you can see, we can add any number of inflows here, so you could have migrations coming in or hires that are not entry level coming in at this point, and then work through the system, and we can plot each of the groups and the total like we did before. So that's pools. Pushed integrators I've already talked about. And then there's one more. And this one is a totally different animal. Totally different way of looking at things, but could be useful. It's using more of a discrete event type modeling methodology, very different from the others. And in this case, we are indeed just looking at one person at a time in the system. Definitely more of a discrete event modeling paradigm. So in this case, it's allowing you to get into the detail of simulating the process of looking for a new hire, screening the new hire, going through that whole process if you wanted to, the delay time it takes between finding a good hire and accepting their offer, or them accepting your offer, and etc. All that stuff. If you wanted to model all that kind of detail, then maybe this discrete change method is the one. Let me go in there. Oh, and by the way, it's in a different kind of container too, because when you're working with one person at a time, you're not just dealing with a lump group of people that might come in over the course of a year or a course of a time step. Instead, you kind of, time doesn't really matter. So, I mean, time matters. You walk through time, but all you're doing is saying, well, we're just going to use events in GoldSim on every event, we're going to put in a new person. And the time that happens is not necessarily known, right? It could be random. You could say, on average, we're going to hire 10 people per year, but they could be coming in randomly, because maybe the delay time is random. So it is a different way of looking at it, but I used an internal clock on this container because it's going to be generating a whole bunch of events during a time step. And so I checked the box for internal clock. And by doing that, now a bunch of inserted events can occur inside of here and not mess up, well, not add inserted steps for everybody else outside of this container. So just imagine there are a lot more time steps going on inside of this container than everywhere else, because the main time step of this main simulation is 1 year, but we might have 20, 30, 40 events occurring inside of each of the year inside of this container. So now I go in here, totally different setup. So now what we have is we need to define the new arrivals as an event. And so right here we say, okay, new arrivals coming in. You imagine this is an event that is representing hiring new people. And every time it happens, it means we hire one person. We're not talking about a flow of amount of people anymore. We're talking about an amount of events, and on each event, it's always just one person every time. Every event that's occurring inside of this model, we're just dealing with one person every time. But the number of events is large. There might be many events occurring. And in this case, it's random. So what we say here is we have a new arrivals. This is the same input we have for the other methods, but instead of thinking of it in terms of 10 people per year just as a lump moving in, instead, what we're saying is this is happening 10 times per year. It's 10 events per year instead of 10 people. Okay, and it's also average. So we've set this random. We don't have to set this random. We can say regular, but it's random. So on average, 10 events will occur per year, 10 hiring events, but it could be 15 one year and 7 the next year. We don't know. And then we go over to this discrete change where we actually add the person. You can see here the value is one person. We're going to add one person. So that's all very simple, but it's the trigger that matters in this case now. If I go to trigger, you see that the trigger is new arrivals, the new arrival event. So when that event occurs, remember this is many times per year and random, right? We are now going to add one person many times per year randomly, and those will be moved into cohort 1, which is now defined as, if you're doing a lot of environmental system modeling, this is probably an element you might not be using very much, but it's in the delay category, and it's called the discrete change delay. And all it does is it says whatever discrete event, whatever discrete amount comes in, I'll just delay it. And that's all it's doing. So we add people coming in, and then we have a duration that is delayed. And then we use another element that might be somewhat new to you, also in the events category. It's the random choice event. I'll go to random choice. It's the element with a little dice symbol. Again, use the trigger coming off the cohort 1, and that's just on event cohort 1. So again, we're just modeling the events that are occurring, assuming that each event represents a person. Now we come in here and we say, okay, there's a probability that this person that just came into the first cohort, there's a probability that they leave and not go to the next cohort. So this is a very different paradigm than what we had before. Before we're just saying there's an amount, a quantity here, and we're just going to split off a certain amount. In this case, no, it's totally different. We're saying, okay, there's a person that just came in right now. Are they going to move to the next cohort or not? And so you can see here that we are simulating it in terms probably more realistic or closer to what's actually going on in the real world. So this person, we're dealing with this one person that just came in, right? And we're going to say, well, there's a probability that they move on or they continue with us. And so we put the loss rate as just 1%. In this case, it's 10% still. And there's a 10% chance that this output occurs. And if you look at the output of this element, you'll see there are two outputs, loss and graduates. Those are the two we're interested in. Now, yeah, there is another output called last choice, but we don't really care about that. That's just what was picked last. And it's just a number, 1 or 2, 1 being the first choice, 2 being, anyway, we're not so worried about that in this model. We're really just interested in these first two. A loss will be an event. You can see we've lost 9, and then graduates 124. So 124 people moved to the next cohort, and 9 left. So then we come over here to this discrete change, and this is just the way it has to be set up. You need a discrete change to then trigger the events that go to the next cohort. So we're going to add a person every time this random choice picks the graduate. So we just refer to the graduates output of the random choice, and then that triggers an event at the next cohort delay, which then continues on its way through this whole process. And then what's nice about these discrete change delays is that they have an output called num in transit. How many people are in transit, which is exactly the number we need to calculate the total population. Just capture those num in transits to get the total population. And then that way, now we can come outside here and we can compare the total population of all of these different methods. So if I run this model, then we can look at the total populations, and you'll see that they're all sort of close, but they're all different. They're all different ways of doing it. The only major difference is the initial. So the discrete change method, there's not a real easy, straightforward way to say, let's just populate each of those pools initially. So that is one thing to consider that's going to be different. We could probably figure out a way to get that up there, but uh, I didn't go into that level of detail. So that is one difference between the discrete change and the others. But you can see overall it's operating in a similar method as the others. Okay, so that concludes the webinar. You see there are multiple ways of doing it. We do have a couple other ways. If you would like to learn more, I have one that is using linear programming. It's using some matrix math, but I don't know if it would be particularly um, beneficial above and beyond the methods I've already shown you. I can't really think of a way, I guess, unless you had many groups. Another way is a script element, which could probably be best to replace maybe the pool method. It just is more compact. And typically what happens here in these kinds of models is you end up with using many elements, because as you can see, these all require an individual element for each cohort. Well, it turns out that you don't have to do this in individual elements, especially on the integrator method. You don't need to just split this out into multiple integrators. In fact, the first model I showed you is using the integrator method, but it's using an array. The integrator is a vector. So if you open this up, you see that instead of having an individual integrator element for each cohort, we've just used it as a vector. And that's just the way that the push output works in this case. When you define a discrete change as a push type, all it does is it pushes this amount into the first row of this vector in this element. It pushes it into the first row, and then subsequent rows get pushed into the next row down until it finally comes out the other end. So you've essentially just collapsed all of those integrators into one vector. So I would say if you need to compact the, if you have a lot of groups or regions that you're trying to model, it could, the model could become unwieldy unless you vectorize the elements, and so that would be a good use case of using this integrator with the method, with the push method in this case. Otherwise, you could use cloned containers, or just simply copy and paste containers that house all of these elements. So the other downside to vectorizing this in this way is it just is a little bit harder to visualize, especially if you have people coming in and out at different cohort levels, because then you have to bring them in and specify which row they're coming in and all of that. It can be done though. So, all right, so it's almost been an hour. I think I probably talked enough, so I'll just wait around here to see if you have any questions. You can go ahead and just text them to me. Otherwise, thanks again for joining us for the June webinar, and we hope to see you next month.